Okay, in 11.5, we start seeing alternating series. Now, alternating series are ones whose terms flip-flop back and forth between positive and negative. Okay, so we have the harmonic series that we've seen in the past of 1 over n, and that one's being 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. And we talked about that when we talked about even though each term is actually decreasing, it's not decreasing fast enough. And because it's not decreasing fast enough, the harmonic series here diverges. Okay? But what about 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6? Because that's something different, and that's actually called the alternating harmonic series. That's still got n as a denominator, but you need to figure out a way to make this go back and forth. And the easiest way to do it is just -1 to some exponent. Now, obviously, if you want your first term to be positive, then you need, it can be n minus 1, it can be n plus 1, as long as for the first term the exponent is even, and for the second term it's odd, giving you a negative. The next term it's even, giving you a positive, and on and on and on and on and on. Now, is the alternating harmonic, is that convergent? And the answer is actually yes, okay? And here's why. When you're dealing with the harmonic, okay, you're dealing with, 1 plus 1/2 plus 1/3. And you're just hoping, right, that this slows down fast enough in order for it to stop somewhere, but it doesn't, okay? But the alternating harmonic series doesn't behave like that. Because each term is opposite sign, if I go plus 1 and then minus 1/2 and then plus 1/3 and then minus 1/4, since the magnitude of each one is getting smaller, it's not even getting back to the starting place of the previous number. So it's actually converging on whatever this number is right here, okay? And so the alternating harmonic series actually does converge. And the thing is that it converges because they're opposite signs in each successive term and because each term is less than the one before it. Now remember, for regular series that have all positive terms, it's not enough to know that the next term is less than the previous term and the fact that it's going to 0. But for an alternating series, because they will all obey this kind of logic, that is enough, okay? So the alternating series test is actually quite simple. The alternating series test basically says, it basically says, given sigma, n is equal to 1 to infinity of a sub n, okay? Basically, if a sub n plus 1 is less than or equal to a sub n, and if the limit as n approaches infinity of a sub n is equal to 0, if those two things are true, if each successive term is less than or equal to the one before it, and not only is it decreasing, but it's actually decreasing to 0, then the conclusion is that sigma of a sub n is convergent. Okay? So you just need to stipulate that each successive term is smaller than the one before it, and that it's not just getting smaller, because it doesn't help if it's getting smaller towards 1, right? If it's decreasing from 2 and they're all getting closer and closer and closer to 1, that doesn't help. Because if you add an infinite number of 1s, it's still infinite. It has to be decreasing and decreasing toward 0, okay? So let's go ahead and let's do an example. We know -1 to the n plus 1 over n plus 1. Now remember that this over here is related to the harmonic. This one is divergent. But as an alternating series, okay, it's not. So if I have a sub n, and that's absolute value of a sub n, whatever. Usually when you say a sub n, you're not including the negative, but whatever. So n plus 1, and if a sub n plus 1 is 1 over n plus 1 plus 1, or 1 over n plus 2, these two together tells me 1 over n plus 2 will always be less than 1 over n plus 1, and therefore a sub n plus 1 will always be less than a sub n. Okay, first part checked off the list. Now I need the limit as n goes to infinity of 1 over n plus 1, and that is indeed 0. Check. So if each successive term is less than the one before it, and your a sub n, obviously without the -1 to the n plus 1, so basically the absolute value of whatever it is that follows the sigma. If that limit winds up being 0, your conclusion is the fact that it is convergent. Yay, convergence. Okay. Okay, well, let's do a few more. Let's sort of work through this a little bit. Now, n is equal to 1 to infinity of -1 to the n, natural log n plus 1. Now that's basically similar to the previous one. I happen to know that if a sub n is equal to 1 over natural log n plus 1, then a sub n plus 1 is 1 over the natural log of n plus 2. Well, for all n, we do know that n plus 2, natural log of n plus 2, that is going to be greater than natural log of n plus 1. So in the denominator, this one's going to have a greater denominator, and therefore this whole thing is going to be less than. And so I know that the next term is always going to be less than the previous term. Check. I also happen to know that the limit as n approaches infinity of 1 over natural log of n plus 1 winds up being 0. Because as much as natural log slows down the rate at which, like n plus 1 goes to infinity, natural log of n plus 1 goes slower, but it still goes to infinity. So we have both of those satisfied. This is convergent. Okay. Now, basically this -1 to the n, or this -1 to the n plus 1, is not the only way for things to go back and forth from positive to negative and positive to negative and positive to negative. One thing that we know also that goes positive to negative is what? Cosine, right? And we happen to know that if we plug in 1, cosine of pi is -1. Cosine of 2 pi is +1. Cosine of 3 pi, -1. Cosine of 4 pi. So this actually winds up being equivalent to that. Okay? Well, here's the thing. This doesn't, this just basically goes, -1, +1, -1, -1, -1, +1, -1, positive, all the way out, right? That's not actually converging on any one thing because it's basically, and the weird thing about this particular, series is that you can sort of reason it out one of two ways. It's actually divergent, but even Leonhard Euler said, given, even he was kind of like, yeah, well, given the fact that you have 1 minus 1 plus 1 minus 1 plus 1 minus 1, it's all about how you group the terms. Because if you group the terms like this, it looks like the sum should be 0, right? But what if I group the terms like this? It looks like the sum should be 1. Well, that's confusing, okay? But this obviously does not satisfy the alternating series test. Now, the alternating series test will not tell you whether something is divergent. It either will tell you that it's convergent, or it will fail to give, basically it's convergent or go try another test. That's basically what's going on here, okay? So it's inconclusive by the alternating series test right here, but I just at least wanted to show you that those two are synonymous because you're plugging in positive integer values for n, so it's going to be cosine pi, cosine 2 pi, cosine 3 pi, cosine 4 pi, cosine 5 pi, cosine 6 pi, and on and on and on and on and on. Now, what happens if I give you that? Well, here's the thing. That is just synonymous with that, and we've already done that. Okay? That is obviously convergent. Okay? Basically, that is the negative of the harmonic series. Instead of being 1 minus 1/2 plus 1/3, it's negative 1 plus 1/2 minus 1/3. But either way, it's still going to be a convergent series. Well, let's go ahead and let's look at n is equal to 0 to infinity of negative 1 to the n over n factorial. Well, I happen to know that n plus 1, or a sub n, is 1 over n factorial. A sub n plus 1 is 1 over n plus 1 factorial. And except for from the jump from 0 to 1, where they're both 1, a sub n plus 1 is certainly less than or equal to a sub n for all n, so check. The next one is the limit as n approaches infinity of 1 over n factorial. That indeed goes to 0, and we never really had any doubt that that was convergent. If that's convergent and n factorial in the denominator is more aggressive than, it's more aggressive than e to the n, right? Then it should be no surprise that we wind up having a convergent alternating series right there. The alternating series doesn't wind up being all that difficult. It's actually one of the easier ones. It actually winds up coming back huge when we start doing the non-numerical series, the power series. And we'll sort of revisit that at that point. But it pops up sort of unexpectedly, and you have to be able to recognize alternating series when it pops up in these unusual circumstances in order to be able to apply what you know from alternating series. So a lot of this does come home to roost when we actually get to 11.8 through 11.10 and actually start doing Taylor and Maclaurin and all those other type of power series. Now, here's the thing. Let's go ahead and pull this out, and a sub n is square root of n over the cube root of n. And I want to reduce that. That's n to the 1/2 over n to the 1/3. That is actually n to the 1/6. So this can be written as negative 1 n plus 1 times n to the 1/6 once I've actually reduced those and used my rules of exponents to sort of simplify it. That is obviously going to be divergent. Not only does that not go to 0, but each successive term is going to be larger than the one before it in terms of its magnitude. And therefore, it's not going to decrease, it's going to increase as it's going back and forth, and it's not going to converge, it's going to diverge. Okay? Now, the main thing about alternating series that we really need to hit is how to assess error due to approximations of alternating series. That's one of the key things in alternating series that really needs to be understood before we move forward, and it is that very topic that we will devote the second and last video to for alternating series before moving on to 11.6 and the ratio and root test. Bye.